Okay, so we're going to look at running a hypothesis test for paired t-test. And basically, even though this is new, this looks very familiar. We're going to write our null hypothesis, but instead of a mu, we're going to have a mu d for mean difference, because we know we're going to have to subtract two columns of data, okay? And the alternative will be mu d, and it's going to be not equal or great or less than or greater than. And it says define the parameter. And when we define the parameter, it's going to be let mu d equal the true population. And we're going to change this slightly. Instead of just mean, we're going to have to write mean difference. All right, so all we have to do is add one more word. But in the past, we were just working with a mean, so we didn't have to include the word difference. Now we're going to have to include the word difference. Prior to this, when we did a t-test, our t-test looked like t equals x bar minus mu s divided by the square root of n. And we changed it up slightly. We just dropped some d's on it. We didn't need to for the sample size, but this is the sample mean difference, the population mean difference, and this will be the standard deviation of the differences. So the only thing is we had to drop 3 d's on it, okay? All right, so the next thing, we'll enter the data. We'll find our missing components. We'll calculate our p-value. Once we've calculated our p-value, we'll state our decision, and it'll be the same decision. If the p-value is less, we reject. If it's greater, we fail to reject. And then we have our concluding statements, and they look very much the same. The only major difference here, the true population mean difference. All right, true population mean difference. That's where our big statement difference is. Otherwise, this is going to look very much the same. This is the p-value that we calculated in step 8. The alpha is a given, and if we don't know it, we'll use 0.05. And we'll restate our definition. This is our parameter that's in part 2. And this is our alternative hypothesis, which is in part 1. All right, so it's going to look very much the same as what we've done before. So we're going to look at a data list. It says one indicator of physical fitness is resting pulse rate. 14 men volunteered to test an exercise device advertised on television by using it 3 times a week for 20 minutes. The resting pulse beats per minute were measured before the test began and then after. So basically, we have a situation where the resting pulse rate was measured twice. And then again after 6 weeks, after they'd used the exercise device. So we have, and they told us a before and an after. And I usually just like to go before minus after, and I'm going to subtract in that order. Now, they're saying, is there evidence this can reduce this, the resting pulse rate? Well, they're saying that my initial pulse rate should be higher. So I'm going to go ahead and pick a pulse rate. And let's just say I pick a pulse rate of 80. So before reduces to after. So I'm going before minus after. And so let's just say afterwards, I ended up with 60. And they're saying it's supposed to, because they said it was supposed to reduce. All right. Since they said it's supposed to be reduced, 80 is greater than 60. That will give me my alternative hypothesis. So the first one, mu d equals 0. Here's a great thing about it being a mean difference. If we're doing a paired test, it will always equal 0. If we're doing a paired test, it'll always equal 0. And we knew it was a paired test because we have 2 sets of data. The 2 sets of data are equal And for each individual, Alex got measured twice, before and after. Trip got measured twice, before and after. So because we have them for each one of them, we can do a paired test. The next thing, let mu d equal the true population mean difference. And as I said a moment ago, we're going to add a new word, and that new word is difference. True mean difference in resting heart rate. And you have to do this. You have to tell us which order you subtracted. So in this case, we subtracted before and after and the 6 weeks program. Okay. Conditions. In our case, we can just write assumed. Now I wrote them out, and basically we have a random sample. Of 14 people. And I'm sure that if we divided it out, there'd be 140 men in the population. And we also have an independence condition, and then we need to check for normality. So this one, number 4, is our normality. We do by box plot. But for our purposes, for regular stats, we can just write, when we get to conditions, we can write assumed. But I have a problem. I need to start calculating some things. And one of the things I need to do is write down the equation. All right. And since I don't have a good place on this sheet of paper, so I have a bunch of stuff already written down, I'm going to write the equation on a separate sheet of paper. And because it's a paired, I'm going to be writing T equals X bar D minus mu D. And then I have SD divided by the square root of n. And then I need to make a list of all the inputs. So basically I need mu D, I need X bar D, I need SD, and I need n. Well, I know n is 14 because that's my sample size. And you might be thinking, well, wait a second, there are 28. And you're right, I measured 28 things, but I have how many pairs? So n is really the number of pairs. So in this case, n is really the number of pairs. So I have 14 pairs. Okay, but I don't, and I know mu d because we already said, hey, this will always be 0, but I don't have xd and sd. So what I'm going to have to do is I'm going to have to go enter all those data points into the calculator. So I'm going to enter the data points in the calculator by going stat, edit, and I'm going to enter them into column L1. Then I'm going to enter the after into L2. So basically, the before column got L1, and the after column went L2. Because this is a mean difference, we're basically going to subtract all of these. 73 minus 73 is 0. 84 minus 2 is 2. Then I have a 4 and a 4, etc. And I'll do that all the way down, but I'm going to get the calculator to do that automatically because I'm going to need to enter that information into the third column. So here's the way you enter the information into the third column. I'm going to arrow over to the third column and then arrow up so that it's selected. Well, I'm going to subtract before minus after. Well, before is an L1, so second 1 minus second 2. And I press enter. And guess what? All of those values are in. It did it all of them for me. Now that I've done that, I'm going to go ahead and I'm going to cheat just a little bit. I'm going to go stat. I'm going to go ahead and run the test. And we're going to go ahead and run a t-test, just like we had before. I'm going to arrow to the left and press enter so the data is highlighted. I'm going to drop down. Well, we said our mean was 0. My list has to be in L3. Now yours might say L1. Well, if it says L1 or L2, go second followed by the number 3, and it should change it to L3. So now we have the list of the subtractions. Our frequency is 1, and we have greater than, so I need to make sure I have the greater than highlighted. Then I'm going to ask it to calculate it for me. And I end up getting a whole bunch of information, and I'm going to write it all down. But one of the things I get is I get X bar D. X bar D happens to be 2.5714. And I also get SD, which is 2.2434. Oops, I wrote that incorrectly. 2.2434. 2.2434. That does not look like much like a 2. That's a little bit better. All right. So now that I've recorded that, I can go ahead and fill that information into the calculator. And I end up having the 2.57, the minus the 0, 2.24 divided by the square root of 14. Now, also when I ran that, it gave me my t statistic, and it also gave me my p-value. So the probability that I get a t statistic greater than 4.289 equals the 0.0004, and technically 0044. And please remember, if you have a number greater than 1 here, look to see how many decimal places, and it's always going to be 1 less than what they have. They said 4, so you're going to have 1 less, which is 3. So 1, 2, 3 zeros. Okay, so our p-value is 0.004. They didn't tell us what alpha is, so when they don't tell us, we like to use 0.05. Make those the same length. And 500 is definitely, or 4 is definitely less than 500. If it's less, we're supposed to reject. So our p-value is 0.0004. We reject the null. There's sufficient evidence at alpha equal 0.05 to suggest that the true population mean, don't forget the word difference, in resting heart rate before minus after, and we always have to say which way we subtracted, and we subtracted before minus after, is greater than 0. And this greater than, we said it was greater than because our alternative hypothesis was a greater than. But since it was a greater than 0, before minus after needs to be a greater than as well. Okay, so hopefully that will help with this. And the hypothesis test. In the next video, we'll be doing a confidence interval. You know what? Just for fun, even though it's not required, or maybe it's not fun, but we'll do it anyway. We're going to go second stat plot, turn that on. Highlight the box plot that has the outliers. Our data list is L3 because that's where the one with the subtraction is. I press zoom 9, and that's where we ended up getting that particular box plot. All right. And we just look at it and go, you know what? It doesn't have any outliers. It's symmetric enough to say that it's normal. All right. So the next video will be confidence interval. Thank you.